A linked list is like an array list in that it holds a collection of related data, but instead of using an underlying array to store the data, it uses a chain of references. The linked list is a fundamental building block of many data structures, so just like an array, pay careful attention and make sure that you understand how they work. For each item in a linked list, we're going to hold two pieces of information: the item's value itself and a reference to the next item in the list. And this object of items is considered a node. Now, this singular node by itself isn't very interesting, but when we chain it with another node, we form a linked list. Okay? The beauty of a linked list is that we can dynamically add nodes to it by simply updating the reference to the next item. Like this. You can see here that we broke the connection between these two. Whoops, let me get my better colored pen out. Between these two, right? And now it's pointing to here, and this one is pointing to here, and this one's pointing to here. So it's really easy to insert and remove items. Or, on the other hand, we can delete nodes by updating or removing them. Like that. The first node in the linked list is called the front, or the head, while the last node is the back, or the tail. And so you'll see these two terms used interchangeably. So far, we've only looked at a singly linked list, but we also have a variation on that called the doubly linked list. The difference is that we also contain a reference to the previous node in the list. So if we add a few more nodes, we'll get our doubly linked list. And just like our linked list, we can add to our list by adding a node and updating our references. Or removing nodes. So a little more complicated than our original linked list, but it's not that bad. But what does this added complexity do for us that other than add memory overhead for each value that we need to store? Well, it allows us to traverse up and down the list. With our singular linked list, we could only go down the list. But our doubly linked list, we can traverse forwards and backwards. This can greatly speed up search, sort, insert, and removal times, but at the cost of additional memory and complexity. And thankfully, you don't have to implement your own linked list, although I highly encourage that you do so. Making your own version of a linked list will help you to understand the data structure and improve your skills as a programmer. But Java has the list interface, which is supported by both the array list and the linked list class. The list interface says that anything implementing it will offer the get, set, add, remove, clear, and size methods. The interface is basically a contract that says you will perform, at a minimum, these methods. And we're going to talk a lot more about interfaces later, but for now, just be aware of the terminology. The keyword implements is what tells you that the interface, or what interface that the class is implementing. Okay? So you see here, this implements is the keyword, and it's saying that this class right here has a contract that it's going to implement whatever this list interface says you have to implement. I know it sounds confusing, but we'll get into interfaces in a week or two. The really cool thing about interfaces is that it adds a tremendous amount of flexibility to our code. In the past, you declared variables with a primitive type or a class name at the left, like this. You can also declare a variable with an interface at the left, like this. First, you could assign an array list object to iPhone apps,
Then later, you could assign a linked list object to the same variable. The same list method call would do the same kind of thing with either type of collection, but of course, the detailed implementations would differ. This showcases both encapsulation and abstraction, as we don't have to see the details of how something is implemented. And we can always program to an interface instead of a concrete class, like linked list or array list.
So when should you choose a linked list versus an array list? Well, for one, with a linked list, it's easier to find, add, or remove elements that are near one of the two ends, assuming a doubly linked list. So why do you think that is? Well, with a linked list, we have a reference to the head and tail, so we don't have to iterate through the whole collection. Once an element has been found, it's easier to remove it from a linked list because we just have to change a pair of references than it is from an array list where we have to shift all the elements to a lower array indice. However, finding an indexed element is much slower in a linked list than an array list because instead of jumping right to the index position, which can be done with an array, the computer must step in and count from each end or either end until the step count equals the index number, assuming we're starting from the head, or equals the length minus the index number when we're starting from the tail. So remember, with arrays, since we know how much memory each object takes, the index is actually a multiplier for the memory offset. So say that we create an integer array and it's stored at memory location 1000. We would automatically know that the memory location of the six elements, or index 5, by adding the memory size of the integer by the index. Or excuse me, multiplying the memory size of the integer by the index and then adding it to the memory location of the array. This would result in a memory location of, if we started at 1000, it would result in a memory location of 1020 in this scenario, because we are at the 5th index and we're saying it takes 4 bytes to store an integer, so 5 times 4 is 20, which is going to result in memory location 1020. So we can jump right to whatever index that we want. So let's take a visual look at this, comparing an array to a linked list using big O notation. So we're looking at array index 5 versus list get position 5. So as you've seen from the previous slide, accessing an array element can be done in constant time, right? So we have big O of 1, and any of those positions we can get, with one operation. Well, a linked list in memory, it has to jump around, starting at 0, going from 1 to 2 to 3 to 4 to 5, to get to our 5th element, which is the 6th that we're looking for, and that takes linear time, because however big the linked list is, it's going to take that many steps to get there, right? Because remember, big O notation is the worst case scenario. So hopefully this makes sense, and hopefully this helps you understand it. Do you need to know all these programming details? No. But will understanding the underlying data structures make you a better programmer? Absolutely. It will also assist you in developing algorithms to help you solve different problems as well. So we've discussed running different processes or algorithms, and it's useful to know exactly how long something took. And obviously the time to run something is going to depend on the machine that you're running it on, right? So for example, we might want to measure the time to get each element at a random index and then to set each element at different random indexes. So if we look at this program here called list execution times, you can see that we have a couple different things going on. We have 2 different indexes, and we have an array of size 1000, right? And we have an array of doubles called list, and then we also have a linked list called list. And here you can see that we also have the same thing for operation type, to get and set, and to remove and add time, right? And so basically the gist of the program is we are going to run it and compare the difference time that it takes between our array list and our linked list. So if we compile it and run it, you'll see that our array list took 125 nanoseconds on average to get and set 1,000 items. Okay, so now let's run it with the linked list. So now we just got to go through and swap out all of our code, right? So we're going to comment out all the array list stuff and uncomment the linked list stuff. All right. So as you can see, because we're using the list, well, actually, we could just specify a list operator, but instead we're not doing that. So anyway, let's save it and run it. And here you can see our linked list runtime. So to set and remove 1,000 elements, it took 1,673 nanoseconds versus our array list where it only took 125 nanoseconds, right? And that's because the array list allows us to jump to specific things because we already knew our length in advance. We didn't use any of the features of the linked list, which allows us to dynamically add and remove. We didn't do any inserts or anything like that. So that's why the array list is a lot faster.